Hello, welcome to ECO-595 Business Research Methods. In this lecture, we will go over Chapter 17, Confidence Interval and Determination of Sample Size. Let us start with an example. This is about the payment people use during transactions, right? So when we make transactions, we could use cash, check, credit card, debit card, and as retailers, they also need to make sure that they can accommodate various payment methods. Now, you may notice that in recent years, more and more people are using credit cards and debit cards instead of cash or check. In addition, more and more sellers are accepting credit cards and debit cards. So right now, let's suppose Federal Reserve wants to find out more details about this trend. They would like to know exactly what percent of people would use credit card or debit card, and what percent of people use other payment methods. What they could is they conduct survey of depository institutions because that's where our transactions are recorded, and they could ask them to report the number of each type of payment the institutions have processed, right? However, let's think about it. There are 14,117 institutions in the United States. Apparently, the Federal Reserve would not survey every one of them. That would be too costly and time consuming, right? But on the other hand, they would also need to make sure they have a very good sample that would represent the whole population. In addition to that, they need to make sure that the result they get from sampling the population is accurate enough. They want the result to be 95% confident. That is, when they represent the results, they are 95% confident that the result is correct. And they have only 5% tolerance for any mistake. To achieve that, now they have the goal. To achieve that, they need to determine a sample size. So now let's think about it. There are 14,117 institutions in the United States. And apparently, the Federal Reserve cannot and will not survey every institution. But if they want to sample these institutions, how many observations they should take? In addition, how can they ensure that they have enough observations in the sample so that results is accurate enough? So their results would represent the whole population. So based on the techniques that we will learn in this chapter, the Federal Reserve determines that they will need to sample 2,700 institutions in order to obtain a result with which they are 95% confident. That is, they are 95% confident that the result they obtained is good enough to reflect the whole population. And with 95% confidence, that basically means they can only tolerate 5% for error when representing the results. So this example illustrates the usefulness of confidence interval. Actually, when they come up with 95% confidence, they are actually constructing confidence interval. In addition, they can use this technique to determine the appropriate sample size. Okay, but let's start with statistical analysis. There are two types of statistical analysis. Broadly speaking, the first one is called descriptive statistics. Okay, now in chapter 20, we basically talk about descriptive statistics tools where we talk about using table, tablets, bar chart, pie chart, histogram to describe the data. That's descriptive statistics. It's more concerned about describing the characteristics of the population or the sample. What we learn in this chapter belongs to inferential statistics, in which we make inference about the whole population from a sample. That is, we realize that the population is too large or the population is not accessible. So we take a sample. Now, when we take a sample, since the sample is used to represent the population, we need to build a bridge between the sample and the population. After all, we cannot equivalent the sample to the population. Okay, so that's the idea about inferential statistics, how we can use a sample to draw inference, to draw conclusion about the whole population. Now, since we are looking at the relationship between sample and population, we're going to have two terms for them. We have sample statistics. This is variable in the sample or measures computed from sample data. For example, if we got a sample and we calculate the average of the sample, that is called a sample statistic. It is a measure calculated from the sample data, or it represents one characteristic of the sample. Now, correspondingly, we have population parameters, and this is a variable in the population or measured characteristics of the population. That corresponds to the sample statistics. The population parameter is the characteristic for the whole sample. Apparently, if you cannot measure the whole population, then you won't be able to calculate or you will not know the population parameter. And this is why sample is so important, because you can get a sample, obtain sample statistics. Okay, but let me make this clear. In statistics, when we will talk about sample and population, this is the presumption we have. That is, a population parameter, a sample statistic is virtually never equal to the corresponding population parameter. That is, sample mean is not equal to population. This is a very important concept in making inferential statistics, especially about constructing confidence interval or testing hypothesis. That is, the sample statistic is virtually never equal to the population parameter. For example, if you take a sample and calculate the sample mean, right? In comparison, if suppose you have access to the whole population and you can calculate the population mean, you would find that although the sample mean might be close to the population mean, the sample mean is virtually never equal to the population mean. That is, the sample is never perfectly representing the whole population. Okay, but we have to live with that. That's the fact. If you cannot sample the whole population, then you are not getting the real or the accurate population mean. Okay, so what can we do about it? If the sample mean we get is not equal to the population mean, all right, then can we still use sample to make inferences? Can we still use sample to draw conclusions? The answer is yes, of course, with the help of statistical tools. Now, first of all, let me talk about a few measures about the sample and the population. These are the measures that we usually consider in statistical analysis. The first measure is the measure of central tendency. Okay, average or the mean is the most commonly used measure of central tendency. It's pretty much tells us the center of the data. So the mean is basically the average of a bunch of numbers, right? For the population mean, we have a special notation for it. This is mu. We usually use mu to denote the population mean, and this is, at least in statistics, it's kind of like common sense. For the sample mean, we use X bar to denote it. It's also common sense. Okay, and I believe everybody knows how to calculate the mean, right? You just add up numbers up, divide by the size of the sample or the size of the population. There are two more measures of central tendency. One is called median, and the other one is called the mode. They have their specific usefulness. Okay, the mean is not a good measure sometimes. Let me show you one example here. This well-chosen average. So let's take a look at this table. This shows the salary of different employees in the company. Say, for example, right? Look at the numbers. The last one, we see 12 workers earning $20,000 a year, right? And if we go up, we'll find that there's one special person, right? This person is earning $450,000. And the next person, president, earns $150,000, going down like that. Now, if we calculate the average of this table, we'll find that the mean salary in this company is around $57,000. And this is the salary earned by controller. If the company reports this number as the average salary, which is correct according to the calculation, then the information it sends us can be misleading because it gives people this impression that, wow, people in this company is earning a lot. Think about it, the average is 57,000, right? So this information is actually misleading because if you look at the actual data, you realize, oops, unless you are the top people up there, right? 1, 2, 4, 5, 10. Unless you are the 13 top people up there, you will not earn a salary even higher than $20,000 a year, right? So this is the case where the mean is actually affected by extreme values. Actually, this first number, $450,000, is dragging the mean upwards. Okay, so the mean, that's the potential problem with the mean. It could be affected by extreme numbers. If we have one extreme number, extremely large or extremely small, then the mean will be distorted by that. So actually, in this case, a better measurement would be the median. What is the median? Well, actually, the median is the number in the middle when you rank order all the numbers in the sample of the population. Okay? So basically, if you cut the first number and cut one worker here, cut the second person, cut one more worker here, keep doing that until you find the middle one, that is the supervisor who's earning $30,000, which this is more realistic in terms of reflecting the earning in the whole company. Okay, so this is the case where median actually is better than mean. Median, on the other hand, is not affected by extreme numbers because in that way we get rid of the extremes on both ends. Okay, so the last measure of central tendency is mode. So mode is the value that occurs the most frequently. That's the mode measured. Okay. The usefulness is will tell us what is the typical salary. What is the number that all salary tends to occur? It's actually $20,000. In addition, mode could be useful when we talk about nominal or ordinal data because in those cases, if we talk about nominal or ordinal level measurements, we cannot do much calculation, but we could find the mode, that is the category that appears the most in the data. Now that we know the mean is not the only central measure, there are modes and the median. Why we need more? Actually, the next measure we're going to talk about is the measure of dispersion. So here's another example that tells you why we care about dispersion other than the mean. Well, look at these two samples. Let's suppose we have two samples, and here are the two sample data. For both samples, the average turns to be 200, okay? But it doesn't mean that these two samples are the same. If you look at the actual data, you would find that for unit product A, right, the values are closer to 200 than for the second sample, unit product B. These numbers are, look at this one, 150, that's far away from 200. And also 250, 240, 261, they are far away from 200. So apparently, we are looking at two different processes here, right? Although the mean of them are both 200. In this case, the difference is captured by dispersion, and this is why we talk about measure dispersion. Apparently, the first process kind of reflects this type of distribution. We have low dispersion, data according closely to the mean. For the second process, we're looking at high dispersion, data are allocated kind of far away from the mean, so it's dispersed everywhere, okay? So in terms of dispersion, there are three measures as well. The first one is the range, easiest one, simplest one. It's just maximum minus the minimum, okay? This range is not that useful, unfortunately, because only use two values in the data. Instead, actually, we use variance and standard deviation more. Now, for the variance and standard deviations, they are related because the standard deviation is just the square root of variance. They both measure dispersion, and just for notation purpose, we use sigma to denote the population standard deviation, and we use S to denote the sample standard deviation. In case you wonder why we need standard deviation and variance both for dispersion, the reason being, now originally when people try to measure dispersion, the way they come up for the calculation turns out to be squaring the distance, the difference between the observation and the mean. Okay, if you know the calculation for variance, you probably could remember that there's somewhere we calculate the square of something. In that sense, actually, when we calculate the variance, we are squaring the units as well. Sometimes it makes sense for us to talk about square feet. That's okay. But it doesn't make sense for us to talk about square dollars. That doesn't make sense. And that's why we would like to take the square root to get standard deviation, because then we obtain the original unit. Okay? And everything is scaled down to the original measure. And that's one reason we have variance and the standard deviation at the same time. Now, if we talk about inferential statistics, we cannot skip one most important distribution. This is the normal distribution. Okay, I believe you've heard this before. You may have even used it before, or you may know this very well. But let me briefly discuss normal distribution. It's a very common distribution, and this distribution is represented by a symmetrical bell-shaped curve. Okay, that curve tells us the pattern of the distribution. Okay, in practice, in the real world, we actually would find a lot of things to follow normal distribution. Our height, our weight, our IQs, or the wage, all of these actually roughly follow normal distribution in the case that most of us are the average person in the world. There are a few extremes, right? Speak of height, right? Most of us are around the average height for our group. Now, I'm not talking about mixing gender, mixing races, okay? So I'm talking about, let's say, just females, right? Most females have similar height, and there are females who are really tall, there are females who are not so tall, right? So that is a normal distribution. Now, for the normal distribution, we also have some nice properties, okay? So here's a typical normal distribution curve, okay? And the curve, again, tells us the distribution in the sense that under the curve, the whole area is just equal to 1. That means 100% of the observation are distributed along the line here. Okay? And if the measure follows normal distribution, okay, what we could find is if we start from the middle, which is the mean, okay, so this is the mean. Suppose now we're looking at a mean of 100, okay. Starting from the mean, through practice, people find out for normal distribution, if we add and subtract 3 standard deviations from the mean, okay, that range we get includes 99.7% of the observation. So basically, if the mean is 100, for example, and the standard deviation is 15, then if we want to have a rough range of our data of the whole population, suppose we only have information about the mean and standard deviation, and we want a rough range for the whole population. What could be the lowest value? What could be the highest value? Okay. What we could do as a rule of thumb is to add 3 standard deviations to the mean. For our case, that's 145. Okay. And also subtract 3 times of the standard deviation in our case, which is 55. And we can say that almost all observations, which actually is 99.7% of the observations are in between 55 and 145. So that's the special property of normal distribution. That is, we can get a rough idea about the whole distribution with just information on the mean and the standard deviation. And if we do twice the standard deviation, that will be, so if we're doing 2 times 15 added to the mean, subtracted from the mean, that will give us 95% of the observation. The 1 times 15 will give us about 68% of the observation. Okay, why this could be useful? Well, for example, this could be useful for inventory control. Okay, if you think about it, for inventory control, if the manager wants to make sure that there's enough stock to satisfy consumer demand, okay, then you need to ask, what is my typical consumer demand, right? You could calculate the average, daily average demand. Then you say, well, let me make sure I have enough supply from day to day. But then what if one day it just happens a lot of customers goes to your store and purchase the product? Okay, you are running out of stock. That's not a good sign. So to make sure that you have enough stock, you actually would need to make sure that you satisfy the demand virtually all the time, or you satisfy the highest demand ever. How can you find out the highest demand ever? The answer is, well, if you know the average demand, if you know the standard deviation of your demand, you could calculate the upper bound of your demand. That's the highest demand you will probably ever experience with 99.7% confidence. So in other words, if you tell me your average demand is 100, standard deviation is 15, I'm almost certain, or in other words, I'm 99.7% sure your largest demand would be 145. And this will allow you to have enough inventory to satisfy consumer demand. Okay, so that's just illustrates the usefulness of normal distribution as its property. And just because of this, actually, statistically, we developed the tool called confidence interval. In that, we are also interested in providing a range for things like demand, for things like sales, for any other situation where we would like to have an estimate for the population. All right, more characteristics about the normal distribution. It is symmetric, as I mentioned. Since it is symmetric, we find that the mode, the mean, and the median are the same for normal distribution. And for the normal distribution, we consider infinite number of cases. Basically, we consider this to be a continuous distribution. We'll also further define that the area under that bell curve to be 1. That means it's 100% of all observers. We also have a very special normal distribution. This is standardized normal distribution. For this normal distribution, we look at a mean of 0 and standard deviation is 1, and usually denoted by z. While in statistics, whenever we talk about that z distribution, z table, etc., then you should know we're talking about standard normal distribution. And that standard normal distribution looks like this. Just like in a typical normal distribution, symmetric, bell shape, right? But the mean is 0 and standard deviation is 1. Why this is important? Well, because, I apologize for this black and white picture, I took it from the textbook. Because now, one usefulness of normal distribution is to use that distribution to calculate probability, okay? If, for example, for casinos, think about it. They need, when they set up the machine, they need to make sure the probability of any individual playing the machine winning the game to be extremely small. And how could they calculate the probability, right? Well, the normal distribution, so actually any distribution, will be used to calculate probabilities depending on the case we're looking at. If we believe the data follows normal distribution, we're going to use normal distribution to calculate the probability. Okay. How do we calculate the probability? We actually would like to calculate the area under the bell curve. Now, for various normal distributions, look at this one. Look at that one, right? The shape is so different, right? So the calculation for the area under the curve will be all different. And therefore, statistically, we decide let's standardize them. Let's convert them into one standard normal distribution so that we can use this one as a guideline to calculate the probability. So standard normal actually turns to be very useful in practice. Now, given that it's not a real stat course and we don't have enough time to discuss this, I'm going to start the normal distribution discussion right now.